Hello and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Thank you to our viewers from around the world for joining us, and please let us know where you are watching from. Also, welcome into listeners on the podcast version of SETI Live, which is available on most podcast platforms. In a new paper accepted for the astrophysical journal Letters, the atmosphere of an exoplanet known as K2-18b was found to contain carbon dioxide and methane, adding the world to the list of possible Hycean worlds. Additionally, a molecule called dimethyl sulfide, which on Earth is only produced by life, was possibly detected. Please join me in welcoming lead author Niku Madhusudan, an astronomer at the University of Cambridge, to the live stream. Thank you for being here today, Madhu, and of course, welcome.
Thank you, Beth. Great to be here with you today.
So let's start at the beginning. What is a Hycean world and what makes them interesting?
So it's pronounced as the Hycean words,
Hycean, okay.
and the name is a portmanteau of hydrogen and ocean. So this was a theoretical construct we published a few years ago, and it was motivated by our findings that a subset of planets with hydrogen-rich atmospheres and water-rich interiors could in fact have ocean surfaces that could be conducive for life, similar to conditions that we see on Earth. So in summary, these Hycean worlds would be basically planets with ocean-covered surfaces with deep oceans and no landmass at all, and thin hydrogen-rich atmospheres with conditions at the surface of the oceans similar to what are conducive for life in Earth's oceans.
Okay, and how big are these worlds? These are super Earths, mini and sub Neptunes, right? They're larger than our own planet.
Yeah. So it depends on the mass. So these planets can be as big as 2.5 times Earth radius. So the radius of a Hycean world can be up to around 2.5 times, 2.6 to be more precise, for a 10 Earth masses worth of mass. And of course, if you go to smaller masses, the maximum radius will be lower, but they can be as large as 2.5 times the Earth in size.
And so you said that these are a theoretical world. So we haven't definitively found any yet?
So we have candidates, and this planet K2-18b is the first candidate that comes very close to being a Hycean world, which is what we show in the paper. That's what our observations are telling us. So it's a very good candidate, but no, there are no confirmed candidates yet. So there are about a dozen candidates that we hope to follow in the coming years with JWST, but this was the first one.
So JWST has definitely made this a much more interesting search. Right now, you can actually go dig into the atmospheres of exoplanets, which is hugely exciting and a big reason why we were all continuing to keep our excitement for JWST despite the delays. So let's talk a little bit. I'm going to welcome people in, and then we're going to talk some more about this actual planet. So let's see where we've got people watching from. We have people watching from. Oh, this is a global one today. Poland. I think that is Czechoslovakia, Venezuela, France, let's see, Germany, Serbia, New Jersey, California, the state of Georgia, Costa Rica, the UK, British Columbia, Canada, France, Pennsylvania, Uruguay. Wow. What else have we got? The Netherlands, more UK and Virginia and Sweden. Wow. Okay. So a very, very European audience today. Welcome in, everybody. Obviously, Madhu is in England. And so, of course, we had this at a special time to accommodate not making you come on stream at 10 o'clock at night. So thank you to everybody who is here during a little bit more of an unusual time for us. I'm also seeing Oregon and Florida. All right. Let's talk about K2-18b. What did you learn from its atmosphere using JWST?
So what we found was that it's a hydrogen-rich atmosphere with copious amounts of methane and carbon dioxide. and we are talking really large amounts. It's at least like about 1% by volume of each of methane and carbon dioxide, which is a high amount. And then what we did not find was also interesting is that especially we did not find ammonia. We only have an upper limit. We don't have a detection. Now that is important because if in the solar system, all the planets bigger than Earth, in other words, the ice giants and gas giants, they all have hydrogen-rich atmospheres. And in all of them, you see lots of methane, but you also see ammonia. Now, you expect that for a deep hydrogen-rich atmosphere in chemical equilibrium, you expect methane and ammonia to be the dominant carbon and nitrogen bearing molecules at low temperatures. We are talking about Earth-like temperatures or lower.
Okay.
However, in this planet, we saw a lot of methane, but we did not see ammonia. If it is there, it must be there. It could be there at very small quantities, which we are not sensitive to just yet, but it's not comparable to methane by a long shot. Surprisingly, we also saw CO2, which is not very common in hydrogen-rich atmospheres at low temperatures, at least not at that abundance, not at 1% by volume. This combination of molecules that we detected and that we didn't detect means that the only way we could explain that is if you had a relatively thin hydrogen-rich atmosphere and an ocean underneath it, which basically cuts off the thermochemical recycling of molecules like ammonia and gives you the composition that we see today. And that to us was a major revelation. And before that, even just the detection of any molecule in a habitable zone exoplanet, even just methane being detected is a huge deal for the field.
So what's the potential for this world then to host life? That is obviously I'm at the SETI Institute. That is a big deal for us. I'm wearing my Frank Drake equation shirt today. So what's the possibility on this planet? I mean, obviously you can't say anything definitive, but why this world is interesting to us?
So a few years ago, in 2021 and between 2020 and 2021, we wrote a few papers, mostly theoretical, predicting that planets like these could be habitable, especially K2-18b. And that's where we actually came up with this the term Haitian. We introduced that term with K2-18b as a prototype. So in that sense, we already thought that there are some chances that this planet could be habitable. Our findings presently are giving good evidence that there could be an ocean underneath a hydrogen-rich atmosphere, but we would still call that as a candidate because we don't know, for example, we don't know for sure what the temperature of that water layer would be underneath the hydrogen atmosphere. It could be that the temperature is too hot and it may not be habitable. It could be supercritical. So those are that's the level of detail that we are still not sure yet. So we can't say for sure that it is habitable. But what we can say is that it still has the potential to be habitable, which is a very, very exciting prospect, right? Because if you see the history of science overall, right, and I'm going out on a limb here, and if you see the entire history of science, this is the closest we have ever gotten to saying with any level of confidence that actually maybe there is an ocean in this planet which is in the habitable zone around its star, period. And we have detected some carbon-bearing molecules in its atmosphere. It never happened before, and it could not have happened before. We never had the sensitivity. And so for us on the science team pursuing this, that is our excitement, is that we even have like a chance of saying that we have detected a molecule in a habitable zone exoplanet, which is a huge deal.
I read that when the press release first came out, I kind of went, oh, okay, a Haitian world, that's neat. And then I dug into it, and then my excitement actually grew from there. I was like, wait a minute, no, this is actually a very big deal. So I'm so glad that you actually are here to chat with us about it. I'm going to welcome in a few more countries and apologize for saying Czechoslovakia. I obviously gave my age away on that one. Of course, that doesn't exist anymore. So thank you for calling me out on that. I apologize. I've been around a long time, and my geography quiz days, that was still a thing. So let's see. We have people from Indiana, Florida, Texas, India. Welcome in. Pakistan. More from India. Oh, wow. You've got an audience here. Spain. What else we got? Brazil, Nevada, Colorado, New York, Iraq, Austria. Okay, this got more global. Oh, North Carolina. Okay, boy, wow. Mexico. Whoa, okay, all right. Everybody from everywhere today. All right, fantastic. So thank you, everybody, for being here. I am speaking with Nico Madhusudan. We are talking about Haitian worlds, and in particular, an exoplanet called K2-18b, where we have found carbon-bearing molecules, carbon dioxide, methane, and so this is a big deal. And but there's another piece to this, isn't there? So there was a little kind of like, it was almost hidden in the press release, because, and I understand this is still sort of an under investigation result. So everybody, I want to tamp everybody's expectations down. But you also found possibly a molecule called dimethyl sulfide. So tell us about dimethyl sulfide and why this result, if it's confirmed, is incredibly exciting.
Right. So dimethyl sulfide was actually, if you look at the literature on biomarkers in the Earth's atmosphere, in the Earth's context, you usually hear about oxygen, ozone, methane, nitrous oxide, and so on. But you'll also, buried in the literature, you'll also hear about dimethyl sulfide. And the reason and a few other molecules like that, methyl chloride is another one. And the reason for that is that these are molecules that are produced only by life on Earth, like dimethyl sulfide especially. And it's a molecule which so far people have not been able to come up with false positives for. In other words, there has never been like a mechanism to produce it abiotically, be it in any planetary environment, at least in the known literature, scientific literature so far. For all the other molecules, there are. So methane, as much as a biosignature it is on Earth, there are mechanisms where methane can be produced without life, abiotically. Same goes with oxygen. There are studies which show that actually you can get oxygen in other ways, but not DMS. Now on Earth, DMS is very, very low in abundance, very low, almost undetectable if you're looking at from a distance. However, there have been studies in an exoplanet context that planets with hydrogen-rich atmospheres, be it super Earths or Haitian worlds, could indeed have noticeable amounts of dimethyl sulfide, and that it could be observable with JWST. Now, these are predictions from before. We are not inventing this concept in this particular paper. These have been predicted before for hydrogen-rich atmospheres on super Earths, and in our own work before, where we came up with the concept of Haitian worlds, we said that if DMS is there at order part per million level, we should be able to detect with JWST. So that was a prediction. And then we go in, and that was our motivation for searching for that molecule in the first place. So then we look for that molecule in this data set. And actually, if we took the data at face value without introducing any offsets, I'll explain about offsets in a second. But if we just took the data at face value, we actually found that there is a non-negligible evidence for the molecule. It was at a 2 sigma level. And naturally, we were very shocked because we weren't expecting as much. I mean, we predicted it to be observable, but we actually didn't expect to find it on first try at any level of confidence. So that took us by quite a surprise. So we spent months actually trying to make the signal go away. That was actually what we were trying to do all this time, is like we spent enormous amount of trying to just try various combinations to get rid of the signal. And what we did is, within the data sets, it's a technical description, but for each detector, we have two instruments, and each instrument obviously has a detector. In one of the instruments there are two parts to the detector which are kind of separate when they're read out. So what we did is we went ahead and introduced as many offsets as we could between the flux levels on these detectors, between the spectrum. And we found that if we put in enough number of offsets, we could make the signal go away. Right? So we could make, like, in terms of a pure statistical robustness test, we could show that we can have like detection significance less than 1 sigma, which means not a significant evidence. Even then, though, even in that worst case scenario, if we actually look at the posterior distribution, is what we call, when you retrieve a parameter, you have a distribution, a histogram of that parameter, which tells you how you're estimating it. Even when we get rid of the detection significance entirely, the posterior still shows a peak at a non-negligible DMS abundance. And that is different from what we would see for ammonia, for example. Ammonia doesn't show any peak. We don't detect it, and you see the histogram, the posterior, as a non-detection. So there's a difference in the shape of the posterior. And so all of these things together give us some hint that it could actually be there. Either that, or we are probably, like, we don't know, we could be misinterpreting the molecule. There may be other molecule that we are not considering in the molecule, maybe something else. So we are open to the possibility that could go away, and we say that as much in the paper, is that there are any number of ways someone else or we ourselves could come in the future and say, what, like, that molecule wasn't there to begin with. We're open with that. But as we tried, we couldn't get rid of it. So
I love that. I love the we tried to get rid of the result. We just tried to make it not appear. That is an interesting way to do it. So this is one of the things I love about science is you guys have this result, and there's parts of it that you're 100% certain of. This is definitely a detection. And then there's this one where you're like, well, we would love to be certain of it. So we know that we kind of have a bias here, and we've tried to not detect the thing, but now it's up to everybody else to replicate analyzing the data from JWST and see if they find it, or they go, no, you don't. And that's how science works, right? Yeah. That's the whole point of it, is that you're supposed to be able to replicate someone's results or tell them, no, they're not at all. Yeah. So I love this. Okay. I think I saw a few more countries, so I just want to kind of welcome people in. We have a few states too: Illinois, Texas, Switzerland, Quebec, Canada, Croatia, Finland, Kosovo. Okay. And so that's, we have a lot. Yay. All right. Where do you go from here? What's next for K12 or K212B?
K218B. Yeah.
K218B.
So actually on this particular molecule, so I think methane and carbon dioxide are quite robust, and future observations could verify it pretty easily. For DMS, on the other hand, there are more observations coming. So we will obtain one more spectrum at another region of another wavelength range. There is another team that will also observe the same planet. So within these observations, sometime next year, we should be able to obtain better constraints on whether DMS is actually present, or it could be some other molecule. So that we'll know for sure. So there is no need to make too strong claims for it just yet. But I think the fact that there was some hint was worth mentioning, because it is such an important finding if it is true, and that should motivate us to put all our resources towards confirming or refuting that particular result. It is a result worth putting all our resources in.
That I'm very excited for you. We are getting a few audience questions in, so I want to kind of work my way through some of these. It looks like Maddie has asked this on a couple different platforms, and can we just go through some of the basics on the Hytian worlds again? Is there a minimum size? is the methane gas or liquid, and what is the temperature expected on these Haitian worlds?
Yeah, so the Haitian worlds, in short, are ocean-covered planets with deep oceans and with hydrogen-rich atmospheres. Now, minimum size, it depends on the mass. So if you go to Earth mass planets, they could also be Haitian planets, but the size in that case would only be like maybe 10% larger than Earth, and you could still be Haitian. When you go to very large masses, you go to 10 times Earth mass, then your size is going to be obviously higher. It could be above 1.5 times Earth size. So the size depends on the mass. And then whether the methane is in gas or liquid. Methane is definitely in gas phase in the atmosphere. The atmosphere is cold. It's like Earth's atmosphere, actually. If you go into the Earth's stratosphere, you see the cold trap where water condenses out. It is literally like that, but that is still too warm for methane to condense out. So methane is in gas phase. What is the temperature on Haitian worlds? They can be anywhere up to the way we defined it is that the surface temperature in the ocean on the ocean could be anywhere up to about 400 Kelvin temperatures, and that is driven like above 100 degrees basically, and that's driven by what we find on Earth is that the extremophiles, these organisms that can live at very high temperatures, go up to like around 120-ish Celsius, which is like order 400 Kelvin.
Okay, so what that comes down to is it's not necessarily life like us, obviously, but there is a distinct possibility that life could exist because we have found life here on Earth that does exist at these sort of temperatures.
That's right.
And types of bioenvironments.
That's right.
Okay. So this is another really good question. I like this. How are we able, and this comes down to JWST. So I'm asking you to explain a bit about JWST, but how are we able to measure all of this with the accuracy that we have now?
Yeah. So the James Webb Space Telescope, what it's doing is that this is a transiting planet, which means you can infer the planet going in front of the star. So when that happens, some of the starlight comes through the atmosphere of the planet, and then some of that light is blocked in the atmosphere due to absorption by the molecules. So we can actually tell how much of that absorption is happening in the starlight. So you get, that is known as an absorption spectrum or a transmission spectrum, amount of light blocked as a function of wavelength. And then we use inverse techniques. These are called atmospheric retrievals, where we take that spectrum and invert it to get the model parameters, which are like these molecular abundances, concentrations, temperature, and all of these are basically free parameters in a model that is fit to the data. So we can extract that information from the spectrum. So that's the method of how we get these atmospheric compositions. And how are we able to measure it with more accuracy? We just need to observe it several more times with JWST. So your data, as you increase your data, your concentrations, these abundances, get more and more precise and accurate.
That actually that leads me to a question. Tell us about what's the star and what's the duration of the orbit, because that's definitely like a thing that you have to be concerned about when you're trying to get this spectroscopic data. Is how often does this planet pass in front of its parent star? How big are they in relation to each other, so that you can actually get that atmosphere? So what's the star? What is K212 like? And or K218, dyslexia, it's a thing. What is K218 like, and how big is this particular world? How often does it orbit?
Yeah, very important question. So the star is a red dwarf, or in other words, an M dwarf star. So it's about 0.4 times the solar radius. So it's half the size of the sun in radius. And the orbit it's a 33-day orbit, this planet around the sun, around the star. Now, because the star is smaller than the sun and hence cooler, the temperature is around 3,500. Because it's cooler, your planet can be closer to the star and still be in the habitable zone, this Goldilocks zone that the Earth is in. For the sun, it's at 1 AU. But for a smaller star, you can go be much closer to the star and still be habitable. So that's the situation with this planet. So even with a 33-day orbit, it still receives like very similar irradiation from the star as the Earth does from the sun. Bolometric total flux. So that's that. And so the orbital period is 33 days. So in principle, once every 33 days, you can see the transit. But then the way JWST is oriented in space, it's not that you can see every single transit. So that has been quite a challenge actually in scheduling observations for this planet. Unlike pretty much any other planet that JWST is currently observing, we can only observe this 4 or 5 times a year. And then there are multiple programs, JWST programs that are aiming for it. So we were lucky to be able to get 2 observations already within the first year of JWST's operations. And here we have the result.
That's very exciting. Yes, there's a stiff competition for time on JWST. Everybody wants to use it. And I'm very excited that you got into some of this early science. And as particularly, I'm guessing from the fact that you used K218b, and that it was a known planet beforehand. Obviously, the K is for Kepler, the 2 is for basically the second iteration of Kepler's mission. So we've known about this planet for a while. Was this at the top of your list for observations, so that when JWST was up and running and you said we want to submit, we're going to just pick the top candidate first?
Yeah, absolutely. I mean, actually, these proposals for JWST observations happened even before JWST was launched. So, like more than a year before that, we were all, putting in our proposals, and there was a global competition for what objects will get observed, and we were selected as part of that process. So and then as soon as JWST flew in the first year of operations, the planet was scheduled to observe, like many other objects, but we had to be very careful in designing the observations such that we get them right on first try, because again, these are non-trivial observations to be making for various technical reasons that I don't need to go into here, but these are non-trivial observations, and the instruments these are being used for the first time in the past year ever, right? So we're all new to JWST instruments, so a lot of work went into understanding in detail how the instruments operate and designing these observations so we could get them on first try.
Wow. Again, the amazingness of JWST and the links that we've had to go to get time on it. Very exciting. We've had so many questions roll in, so I want to make sure I get to a couple more. Okay. Everybody is very interested in this one. Sometimes we get like 2-3 questions. I have 10. We're not going to be able to get to all 10 of these, guys. I just want to let you know, but I want to ask a few of them. Neri is asking, what is the approximate time frame in which we could see the results replicated by other labs? And Ali has also asked, what is required in order to robustly confirm the presence of DMS in the atmosphere? So that's sort of a 2-layer question. What's the approximate time frame, and what is required to make the confirmation?
Yeah. So for the methane and CO2 detections, which are our robust findings, those can be replicated anytime within the next few months, I would think. DMS, on the other hand, no matter who tries it, it's going to be tentative. Some may find it, some may not. You have to do very rigorous analysis to establish that. But even with all the rigor in the world, I don't think anyone will find it to more than a couple of sigma at best, and some may not. Like we ourselves have found various ways in which we can get rid of the signal. So with the current data, in a few months, people can confirm methane and CO2, but definitely not DMS. DMS needs more observations, and that can happen over a 1-year time frame. Our own observations will come by mid next year, so that's one thing. And there is another group which will also observe, most likely. So by this time next year, we should have a pretty good handle on DMS if all goes well.
Okay, I'm going to be looking forward to this. I hope you know, and you may get pinged by me again to discuss some more. Paul is asking, is there any way to verify the results not using JWST? Are there alternatives to JWST that they could use, or is this just strictly a JWST level detection?
Unfortunately, this can be done only with JWST. There is no other way. I mean, we would have done it if there was another way. We would have done it, but sorry, but there is no other way for now.
Again, this is why we hinge so many hopes on this. Okay. Dawid has a couple questions, and one of which is definitely the more serious of them. So we're gonna start with this one. What kind of organisms and in what process produce DMS here on Earth?
So on Earth, phytoplankton in the Earth's oceans produce DMS. And there are also other natural vegetables and so on. When you boil them, I think you get DMS. So basically, but the most dominant source is microorganisms in the Earth's oceans.
Which makes this really interesting because, as you know, the Haitian worlds are essentially hydrogen ocean worlds. So we're talking about an environment where no, you're not getting surface vegetables. There's no land. This is beyond water world, right? Where this is much more than that. So having a mechanism here on Earth that is a valid mechanism on a Haitian world is definitely makes it even more exciting.
Yeah. I mean, yeah, you definitely can't rule out the possibility that, if there is an ocean world out there, that it can produce a lot of DMS. Now, that said, we also need to qualify that we don't know if there is any other process elsewhere in nature that doesn't mimic that same DMS abiotically. Again, that's a theoretical open question. So far, there hasn't been any process, but in the future, someone could come up and say, hang on a minute, there is an abiotic process to get DMS. So that is subject to interpretation at that point. But so far, we can't rule out that you can have biotic processes producing DMS on Haitian worlds.
So I'm just going to point out that actually answered a question in the background. Omar was asking if there was another known process, and we have now answered no, not that we know of yet. Okay. Last question, and I saw this one and I kind of chuckled because this is the thing scientists do in the background, and I like to know about sort of the personalities of the teams working. So Dawid also asked, do you have a nickname for this planet aside from its license plate designation?
Actually, we don't. sorry to disappoint, but we were quite content with K218b. I only now realize that actually that may not be for everyone, it may not be the most appealing name, but no, that's what we go with.
All right. Well, that sounds like we can take some suggestions. So very excited about this, and definitely excited. You all have so many really good questions. Please feel free to go bounce into YouTube and put those in there. I will be sending Madhu the link, and then hopefully we can get some answers to some of those questions. Because we're out of time, and I don't want to keep you from all of this amazing research because you are doing some incredible work. And from a SETI perspective, it may not be intelligent life as we know it, but it would still be a really incredible discovery. So just one last thing, what is next for you? And what are you working on next? Are you obviously more of this, more Haitian worlds, but what specifically are you going to be working on now?
Yeah. No, I would like to first say that with our excitement for possible inference of life elsewhere, that is very exciting in the future. But I think we should also not lose track of the major observational advancement this represents for the entire field of exoplanet science and for science in general. That to us, that is the biggest result, is that being able to detect any molecule, carbon-based molecule at all, in a habitable zone planet. The detection of methane actually solves like a more than decade-long problem in the field. Very few people may know that. It's called the missing methane problem. We had never detected methane in a habitable zone exoplanet before. So this solves a big problem in the field. So there is that. And then the takeaway message, as far as we are concerned, if we want to talk anywhere near the inference of the ocean and the possibility of DMS to be confirmed before, the takeaway message is that we as a species, now forget about us as a scientific team that has found these things, but representing the whole species, we want to be open for habitable environments that could be very different from that on Earth in our search for life elsewhere. That is my takeaway message. And what is next is that, well, we are at it. We are going to observe K218b more. We have several other planets, also Haitian candidates that have lined up and that have JWST data coming. So we could prove or disprove some of those. So there is much more happening on this particular area in our search for habitability and biosignatures elsewhere over the next couple of years.
I am very excited for you and your research team. Congratulations on these results. These, as you pointed out, these are massive results and kind of very groundbreaking. So I'm very excited for you. I'm looking forward to more of your research. And obviously, Madhu, thank you for being here today. Thank you for taking time and for doing this. I greatly appreciate it. The audience has thoroughly enjoyed. Someone is asking you to name the planet in honor of me. Please don't do that. Please don't do that. I appreciate the thought, but no. So, go and have a wonderful rest of the day. Thank you, everybody, for being here and watching and all of your fantastic questions. And I'm so sorry we couldn't get to all of them. You really do have a lot of great questions in the background. So again, please wander off to, if you're on Facebook or YouTube, please, leave your questions there. And I will make sure that Madhu has the links so he can always come back and try and answer some of them. I put a link to the paper in the description of the video as well as in the chat. So, go take a look at the paper. It's the preprint. It's open access for you on that. And eventually the publication will be open access too. So thank you so much again, Madhu, for being here and for taking the time. And thank you everybody for watching. And this is SETI Live. We are the SETI Institute, a 501c3 nonprofit. So as always, I'm making a pitch for you to go to SETI.org/give now and donate to keep these wonderful outreach programs going so that I can invite amazing scientists like Madhu on to discuss their work with you and let you in on some of this great science that's being done. So, if you have the opportunity, please support us. And of course, go check out Madhu's work. And we will see you all next week. I will have another fantastic interview for you. So everybody have a great rest of the day.
Thanks a lot, Bev, and thanks to all your viewers. Have a great rest of the day.